Welcome to this lecture on consumer decisions discounting through time, where we look at the standard economic model of making intertemporal choices and discounting through time. First up, I want you to think about this basic question here. This question has been asked in different surveys, and it says that assume that you deposit $4,800 at the end of each year into a retirement savings account that earns 10% yearly rate of interest. How much money will you have in your account after 40 years? You can do some basic math in your head and try and come up with an estimate. And when this survey question is asked of average people, the median participant guesses right around $223,000, which seems like a reasonable guess because you have 40 years of savings of around $5,000, but you can round up to $5,000 because there's some interest in there. And that gets us to $200,000. But then plus we have a little bit more interest than that. And so we get up to $223,000 as a median guess. This guess, though, is very insufficient. It is a very lowball guess. If you actually do the math, the actual answer is right around $2.3 million. That is the value of compound interest and the incredible power of that concept. Compound interest, it has been said, is the eighth wonder of the world. He who understands it, earns it. He who doesn't, pays it. If the theory of comparative advantage is the most powerful force in economics, then the theory of compound interest is one of the most powerful forces in personal finance. People often err in personal finance decisions by not understanding this power. So what we're going to do is we're going to work our way through the power of compound interest. We're actually going to break down some of the math so that you can see where that power actually comes from and how it's generated. And we'll be able to see elements of equations. And then what we're going to do is we're going to take those elements and put them into all different kinds of equations to help us understand the economic model of man in discounting through time. We'll have different equations that can represent how man would discount if he was rationally looking at payments on into the future versus payments today, or what money could become if he took into consideration this power of compound interest. So let's see this power of compound interest and see how we can more easily calculate this. So a little question for thought here for you to start us off. How long does it take you to double your money if you invest in a fund that gets 8% returns each year? We can go through and we can do the math to this. At year one, what we would do is we would say, okay, well, we put in $100 and we take that $100, but to it, we also get interest. We get 8% interest. So we get 8%, 8% of what? Well, 8% of what we put in. So we get 8% of the $100 that we put in. So we have the starting point of, hey, we put in $100, but then also we get 8% returns on that $100. And we need to add those two together, which gives us our total of 108. And that's after year one. But what happens after year two is where this power of compound interest comes in. We no longer have $100 as our starting point in year two. We now have the answer to, well, what did our money become after year one as our starting point? A year has passed and we've earned 8% interest. So now we start with $108. So now it's not just that we have $108 to start with, and so we're going to add to that, but we have $108 to start year two, and we are going to get 8% interest on $108. Not on $100, but on $108. Well, this seems to not really matter that much as we add the interest that we earned to the original 108, and we only end up with 116.6, which is really just adding $8.60. So in year one, we added $8, but in year two, we added $8.60. Doesn't seem like much of a difference. Go to year three, and what do? You just continue on with this process. Our starting amount of money, right, is now what we finished with from year two. And then we get interest off of that starting amount of money, and we get our outcome at the end of year two or end of year three. The start of year four takes the end of year three, and so on and so on and so on. And you can see here by the move to year 5, we're not just adding $8. We're not just adding $8.60. We're adding $10.90 now. So the amount that we're adding is growing and growing and growing. Why? Because the interest that we're earning takes into consideration not just 8%, but 8% of the original amount. And the original amount comes from growth from the previous year. After 6 years, we could be up to 158.7, 7 years, 8 years. Finally, at 9 years, we've basically doubled our $100. When we're earning 8% interest, after 9 years, we'd basically double our money. We got really close to $200. So we can think about this basic formula of compound interest here. What happens? Well, we can start with this idea that the interest rate we can state as a lowercase r. What we'll do is if the interest rate is 8%, our r equals 0.08. The initial principal is A. So in this case, our initial principal was $100, so A equals $100. After one time period, what did we have? Well, the value of this investment that we made, where we put $100 down, was $100 plus our $100 times the interest rate. Or after time period 2, what was it? It was 108 times, or plus the 108 times 8%, right? And so we always have this A plus A times R going on, right? So we're always working within that kind of framework. Well, it helps us out in future formulas to actually rewrite A plus A times R as A times 1 plus R. We're going to see a 1 plus R all over the place. That's trying to factor in this idea of compound interest and the power of it, right? You can see that this is exactly the same. If we did A times 1, we get A. And then what we have to do is we have to factor this through, and we have to say A times R gives us A times R. And what do we have to do with those two terms? Well, we have to add them together. So it's just the basic properties of mathematics that shows us that these two equations really are the same thing. We're not switching to some new equation. We're just rewriting it because it's going to have nice properties for us to have this new approach with this A times 1 plus R. So let's add to this. After 2 time periods, we don't just have A times 1 plus R, which is what we have after 1 period. What we can also do then is multiply that by 1 plus R. Now, this seems kind of weird, but if you think about this, right, what do we have here? We have a situation where we have, let's say, $100, and we're trying to see after 2 time periods what it's earned with 8% interest. We say, hey, we have this $100 times 1 gives us this $100 plus A times R. 100 times this 0.08 gives us this 8. And so this term right here, this white, right, gives us an answer of 108. That's what happens after 1 time period. Well, now what we can do is we have to then multiply this through by the rest of it, by 1 plus R. Well, 108 times 1, right? If we do this, 108 times 1 gives us 108 plus, we have to do 108 times the R. The R is the 8%. So what we're going to get is we're going to get 108 times the 8% gives us 8.6. And lo and behold, we get this 116.6, which is exactly what we said we should have after 2 time periods when we did it 1 at a time, 1 at a time, 1 at a time, 1 at a time. And so what you can see from this is if we want to add another time period to this formula, all we have to do is simply just keep adding these red parts of the equation here, this 1 plus R. So we can just, if we want to do this after 3 time periods, we would simply multiply by 1 plus R again. And with 4 time periods, we could do it again. And 5 time periods, we could add or multiply 1 plus R again and again and again and again. We could just keep adding that on. So what we can see is that this should be rewritten as A times 1 plus R to the T. T being how many ever time periods we want this to go. So if we want it to go 4 time periods, we can simply do A times 1 plus R to the 4th power. So the value at the outcome of a compound interest formula is equal to the principal times 1 plus the interest rate to the power of how many ever time periods we're looking at. A shortcut for looking at the power of compound interest is called the rule of 72. The rule of 72 is a rule of thumb used to estimate, given a constant rate of return, how long it will take for a value to double in size. Basically, all that you have to do is think about, well, the time to double is equal to approximately 72 divided by our interest rate or growth rate. Here's that equation. Again, the time it takes for your money to double is approximately equal to 72 divided by whatever growth rate you have, or whatever interest rate you could be earning on the money that you invested, say. So as an example, we can see a rule of 72 would be that if we had 2% growth, it would take us approximately 36 years to double the money. 72 divided by the growth rate of 2% gives us 36. If we were growing at 1%, wealth takes about 72 years to double. 2%, we just said, was 36 years. 4% takes about 18 years. 8% takes about 9 years to double. 72 divided by 8 gives us 9. Well, that was actually the problem that we started off with. We had 8% growth and we had $100, and we wondered how long it would take us to double our money. When we did the math, we showcased that it took 9 years to turn into $199.90 some cents, basically doubling. The idea of this exponential growth is often hidden from our normal way of thinking. People often fail to save and proceed to borrow more than they should because they underestimate the power of compound interest. As the African proverb states, the best time to plant a tree is 20 years ago. The second best time is now. So let's look at the power of annual contributions to our outcome. So say we now only have just $100 to start, and then we see what it turns into with the power of compound interest. But we have $100 to start, and we make an annual contribution of, say, $50 each year. And we want to see what that becomes with the power of compound interest. So let's start adding to our formulas here. So here on this one, what we want to do is we want to think back to our compound interest formula. Remember, after 2 time periods, it was a times 1 plus r times 1 plus r. And we said we could rewrite this as a times 1 plus r to the t, so that our equation for the value of compound interest is the value of is equal to a times 1 plus r to the t. When we do the compound interest formula with annual contributions, we need one more symbol. We're going to add in the idea of the annual contribution of C. So if we make the same contribution each year, we can have the symbol C represent this, and we can have an equation, which we're not going to break down, and it's pretty tough to completely understand, but it's worthwhile knowing that this equation exists. Your continual contributions, if you make them, become A times bracketed 1 plus r to the t, unbracketed, plus c, all that's in there, times all of these brackets, 1 plus r to the t plus 1, minus this 1 plus r bracketed divided by r. So if we have $100, we can put that in for our A here. And if we knew the interest rate, say it was given to us as 0.08, and we knew the time period, let's say for 7 years, we would plug that in for our t. And if the annual contribution was $50, we could just continue on and plug in for all of the other variables that we already know. And as long as we get our equation right with the parentheses and all of that, we will get the outcome that we would get of compound interest with this continual contribution. So this is the equation for making continual contributions and doing the compound interest formula to see what, if we put money in now, what does it become? What we're going to do next is net present value and present discounted value ideas. Time is money, and the theory of compound interest, time is a lot of money. Money now is worth money on into the future, right? If we have money now, what we can do is we can theoretically invest it at some growth rate, an interest rate, and it will become more than it currently is. $100 at 8% interest can double in just 9 years. So what we want to do is we want to think about this and how we can move in multiple directions with, okay, what does money into the future mean for money today? And what does money today mean for money in the future? With net present value and present discounted value calculations, we're actually moving in this opposite direction. No more are we looking at how much money today turns into on in the future. Now we're looking at how much are payments in the future worth now. These ideas are very important when you're making big, expensive decisions. Do this wisely by considering how money now is worth different amounts than money into the future. $1 today is not the same as $1 tomorrow. When we think of present discounted value and net present value, there's one major distinction between the two. A present discounted value looks at some future amount of money and it brings it back, it discounts it back to what it would be worth today. It does the opposite of that compound interest question. Instead of $100 becoming $108 a year from now, what we're doing is we're saying, hey, if I got $108 a year from now, and there's an 8% interest rate, how much is it worth to me today? And the answer would be $100. Present discounted values look at future values and say, how much is that valued at today? Net present values do exactly the same thing, but our outcome is netted. It is taken into consideration both benefits and costs. And thus, we can compare our result to an answer of 0. If the net present value is greater than 0, then that means that the benefits on into the future are greater than the costs on into the future. If our net present value is negative, then we can see that our future costs and benefits end up with more cost than benefit. This is the main distinction, though I have listed here much for you to think about and how the present discounted value is slightly different than the net present value and when you should use them. Go ahead and pause the video and read through if you want to try and understand what I just said in different words. So let's look at the present discounted value formulas. First up, we want to note that what we did when we did the equation for compound interest was we took the value will become, is this V of t, was equal to the amount we originally had in today's money times this 1 plus r to the t. Well, what we can see is that the present discounted value equation shown below is really the exact same equation, but we're just solving for a different variable. We have different information. Now we're given this V of t. We're given some money value on into the future, but we don't know how much that's worth today. We don't know what that value A is worth, right? And so what we're going to do is we're just going to rearrange this equation. We're going to divide each side by this 1 plus r to the t. That will eliminate everything on the right side of the equation, and it will mean that the left side of our equation, our top equation here, is just divided by this 1 plus r to the t. So the V of t, the future value, divided by 1 plus r to the t, equals the current dollars in today's term, the current principal that would be equivalent to. Well, that's what the present discounted value is. It's just a fill in for that variable A, but we don't know how much money we have, and so we're solving things through backwards. So present discounted value is essentially like solving this top equation, but solving it for A. We just call that our present discounted value because what we're doing is we're taking that future payment, we're discounting it through time and seeing what is it now currently equivalent to in today's dollar terms. We can do this over multiple periods. We can break this down by multiple periods. We can see that the equation we just did for time period 1, the value of time period 1 divided by 1 plus r to the 1 time period, would just be the value, the present discounted value for what happened after one time period. but then we can add that to other time periods. It's the same equation, but we just add it in with a different time period. It could be the second time period, or it could be that we get some other payment at, say, not the second time period, but at the 22nd time period. So we get a payoff at time period 1 and a payoff at time period 22. We can calculate the present discounted value of that by simply adding these two together. And so you can see a representative equation here of what you would do when you get multiple payments into the future that you want to discount into today's monetary terms, or the present discounted value. If you have a constant payment stream that is occurring on into the future, we want to look at how much that is worth in today's terms. So we can look at our now variable m, which will be this contribution, this continual contribution that we get from this payoff. So it's your grandfather says that over the next 10 years, he's going to give you $1,000 each year, right? Each year you get that contribution, that amount m. You have this equation here, m divided by r, multiplied by this 1 minus 1 divided by 1 plus r to the t. That becomes the present discounted value when we have a constant payment stream. Those contributions have to be equivalent at each time period. So we have to be getting $1,000 each year. It can't be $1,000, then $3, then $30,000, then $10. It has to be this consistent contribution, and we can just simply use this equation here to say, okay, that future current of payments, that future stream of payments, what is it worth in today's terms? An extreme example of this is called a perpetuity. A perpetuity is just a payment stream that goes on infinitely. So you get these continual contributions. Instead of your grandfather saying, I will give you $1,000 for the next 10 years, he says, I will give you $1,000 for forevermore, right? Even after I die, there's an account set up where you get $1,000 each and every single year. How much does that become, right? How much is that worth in today's terms? Well, what happens is we have that same formula we just had, at least the start of it, but then the end part of it here, all of this stuff that was over here goes away. And the reason for that is that what we end up with is the infinite term filling in for our t time periods and making the outcome of that equation very, very small. So you end up with a 1 minus a very, very small number. So the outcome ends up basically just being 1. So you get a times and then roughly 1 here. And what are you going to end up with? Well, just this m divided by r. So what's really cool with a perpetuity is it sounds like it would be a lot harder because it's an infinite number of time periods, but it actually ends up being even easier, where the present discounted value of this future payment stream for an infinite time horizon is just m divided by r. Now let's turn to net present value formulas. This is going to be very similar to the present discounted value formulas with just one exception. That exception being we will also add in costs. Net present values look at netted outcomes, where we consider not only benefits, but also costs. So here, instead of just having some value that we put into our equation, right, instead of it just being v of t and having this be pdv, right, we just change that out. Instead of it just being the value, we have benefits minus costs. And it's now no longer equal to the present discounted value. It's equal to the net present value. So this equation should look eerily familiar. It's the same one as the present discounted value. And as we said when we talked about the present discounted value, that is the same as the compound interest formula, just solving for a different variable. Here, again, we can kind of amend and morph and use this concept to go further with net present value calculations. For instance, just like with present discounted values, if we have multiple time periods, what we can do is we can basically just kind of segment our equation into different time periods. We can say, oh, at time period 1, we had certain benefits and costs, and we can adjust that down and to today's terms, to how much it's worth today. And then we can say plus some payment that we get at year 2, or some cost that we get at year 2, or some combination of benefits and costs that we get at time period 2. And we can do this with as many time periods as we'd like. We don't have to have time periods that are consistent and in a row. It could be time period 1 is here, but again, it could be that time period, say 21 is here. And we would just change the formula so that's this B1 minus C1 divided by 1 plus R to the 1 plus, oh, we had some benefits and costs at time period 21. So we have this B21 minus C21 divided by 1 plus R to the 21st power. And so this is just kind of a representative equation again of what you can do with net present values that occur at different time periods. You can have benefits and costs throughout and discount them into today's dollars, and you can net them out. One thing to remember is that if we have a benefit or a cost at time period 0, you do not want to discount that at all. You're trying to turn everything into today's dollars. Well, if it occurs today, it already is in today's dollars. So what you can do is anything that happens now, you can consider as happening at this 0 time period, and you do not have to discount that. There's no dividing by 1 plus R to the t. All you're doing is just saying, oh, we could have some benefit, some cost right now. It's already been discounted. It's in today's terms of dollars, and so we don't have to do anything to it, right? There is no discounting. It is what it is. It is already in today's terms. So you can just add that to the start of the equation, and that makes it real simple. Okay, so here I have a basic equation summary sheet. You can look at the equations that we just went through, and we can see the different setups that we have. You can see how they're all kind of consistent with one another and where they differ a little bit. And you can use this kind of as your guide through these different types of discounting of payments from the future to today, or as we do up on this part here, taking money into today and seeing what it will become. Here from this, we get this idea of the power of compound interest, and we start to harness it a little by understanding how it impacts the amount of money we have and how much we could have on into the future. So one final question for thought. I love this as a practice question for you. This is a little bit harder than just plugging into the simple equations that I showed you, but you can solve this with the equations that were just given to you. You need to do a little bit of thinking. You can't just plug it into one equation. You have to kind of manipulate things and perhaps plug into one equation and then into another to figure out what the outcome is. But what you're going to do is you're going to figure out who has more money at the retirement age of 65 from their retirement account, assuming 10% returns. The question asks you to figure out who gets more, Jeremiah or Tom. What you'll see is that actually Jeremiah ends up with more money, even though he only invests for 8 years. He invests for 8 years, but he leaves it invested, and so he takes on the power of compound interest for quite a long time. Whereas Tom, he doesn't start investing until Jeremiah is done investing, but he invests a lot more often. He invests not just 8 years, but for 38 years. But because he didn't start as early, he doesn't take advantage of that power of compound interest as much as Jeremiah did, and so he doesn't quite make as much as Jeremiah. See if you can come up with the exact numbers and see how that works out, and you understand the equations that we have been using so far, if you can do that and do that well.